All right, welcome to the Grasp on Robotics Talk series. We've got a special one today, even though the semester's over. So my name is Mark Yim. I'm the host for today's talk. Just as a quick reminder, previously recorded talks are available on our YouTube channel and website. If you're joining by Zoom, please just submit your questions by the Q&A button. Actually, you can't unmute. If you do unmute, the speakers are broken here, so we won't hear you. When you submit your questions, we'll have our panelists submit your questions, and we'll go from there. We've got two panelists today. Spencer Folk, a PhD student, co-advised by me, Ani Shea, and Vijay Kumar. And we've got Fernando Caldera, who's also co-advised by Ani, Vijay, and CJ Taylor. Spencer is a PhD student who is interested in exploiting wind for navigation of flying vehicles in urban environments. Fernando's interested in a variety of machine vision techniques for robotics and a bunch of other things. I forgot what the other things were, but that's okay. So, we are here for Pauline Pounds, who is, I met actually 10 years ago when she was, I believe, a postdoc at Yale at that time. She's now an associate professor at the University of Queensland, did her PhD and undergraduate at Australian National University. She's got the Batterham Medal. She received that in 2020. She specializes in kind of innovative, creative flying vehicles and some legged vehicles and sensor stuff. All the stuff that I've seen is really super interesting. And she's going to talk about that from the past 10 years. Please welcome Pauline Pounds.
Thank you very much. And yeah, it's been about 10 years. And I reflected when I was invited to come and talk that it's an interesting juncture, having looked back at the last 10 years of the work that I've done. I thought, actually, I've done so many different things. I try to give you a bit of a flavor of everything. So this is an exercise in colossal breadth and less so in depth. So if you get a little bit of genre whiplash as we go from topic to topic, please just lay down on the floor if it all gets too much. So I'm going to talk to you today about drones, bipeds, and sensors, 10 years in the UQ Robotics Design Lab, and in particular the ARG, the Aerial Robotics Group, of which I am the lead. So in fact, see if that pops up. Yep. So in fact, I'm one of a few people who are members of the UQ Robotics Design Lab. We were founded back in 2012 after a whole bunch of robotics folks left to start a new lab at QUT. And when a great oak falls in the forest, smaller trees may spring up in their place. So Surya Singh and I started our group, and then we added Hannah to our ranks. And Surya is doing amazing stuff in robotics control. In fact, he's so amazing, he's been poached and he's now at BDAI. He's gone to the promised land. And Hannah has gone on to RSCS at ANU, where her work in decision-making under uncertainty is very much appreciated. And Zhenjian Chung, formerly of ETH Zurich, has just joined us, bringing us back up to something looking like full strength. So I'm the aerial robotics side of UQ RDL. And we look at practical whole systems approaches towards robotics design. We look at UAVs, we look at sensors, we look at walking machines, we look at industrial applications, lots of different places where we can use our special little set of toolbox. And our toolbox is mechatronics, dynamics, and control, and not CS. So if you're looking for an algorithm, I'm sorry, I can't help you. I'm terrified of anything with an operating system. But if you're interested in dynamics, control, and mechanical systems, oh boy, that's what I'm all about. So here's a little grab bag. Some of these you'll see today and other ones will remain conspicuously elusive. So when last I came and visited, this one hasn't quite put the video through properly. I might actually reshare the screen just so that you can see the, oh no, it's picked up. So when last I visited Grasp Lab 10 years ago, I was showing off some work we'd done at the similarly named Grab Lab at Yale, where we did some of the foundational work on aerial manipulation. And I very much enjoyed this work because it had a clear practical application to underlying theory that relied entirely on clever mechanical interactions rather than on high-speed, very efficient algorithms or robot thinking too much about what it was doing. And this sort of set the pathway for where we went in the future. So if you haven't seen it before, go check it out. It is kind of cool. The very first object delivered by a hovering drone, by the way, was a can of Guinness. So I think that says a lot about our work in philosophy. So what do we care about aside from cans of Guinness? Making drones cheaper. We want our drones to be low cost, so cheap that we can even throw them away when we're done with them. We want to make drones better. We want them to fly longer, further, carrying heavier payloads, and just generally being more capable. We want to make our drones safer. We want them to be able to reject wind gusts and perhaps sense obstacles around them, and a brief detour into stopping humans from being cut to ribbons by them as well. And we want to make dynamical bipeds affordable. This is a new branch for us. It's kind of odd to work on something that doesn't fly, but actually a lot of the principles are very similar. So my stratagem is to radically rethink and reframe problems to find electromechanical, what I call stupid or dumb solutions, instead of CS-based smart solutions. And not only is it because I'm not that great at CS, but it's also because there are many benefits from going for a hardware-centric solution. They're simpler, they're cheaper, they're faster. In terms of response time, there's no sampling involved. They'll involve fewer parts, and what's not to love? Anything you can do to make your system more practical and employable, the better off you'll be. So when I started my position at UQ, I had $50,000 from the university and their well wishes. I had no space, no money, no people. Yeah, what do you do? Well, in this case, what can you do except start with what you've got around you? And if there's one thing a university has, it's paperwork. So I thought, can I build drones out of paper? And the answer is actually yes. In fact, paper is a well-loved and well-regarded form of amateur aeronautical development. And I think everyone here will have made a paper plane at some point in their career. So we thought, well, if we've got paper, can we turn that into a drone? Because paper's really cheap. Humans have been making paper for thousands of years. And the answer is yes, actually you can. If you build a really simple circuit board and stick it on your drone and add some voice coil actuators, you can build a pretty serviceable drone, so long as all you want to do is glide. But you can build a better drone if you think a little bit more about the aerodynamics of that structure, going from just a delta glider to having something with crenulations in the airfoil based on what a dragonfly wing has, allows you to get a more efficient shape and also a stronger shape. And we also explored opportunities to use recycled materials, such as egg cartons. If you pulp up a whole bunch of paper, crush it into a shape that looks a bit like an airfoil, maybe you could build something that flies. And the answer we found was sort of. The density wasn't working in our favor there. But it's not just enough to build the structure of an aircraft to be cheap. Can we also make the avionics that make it fly cheaper? And so we devoted a bunch of time building circuits onto paper and seeing how well we could make something that could actually run a circuit to drive the aircraft and guide it. And the answer there is, oh, not really. And our very first effort used surface-mounted parts that were effectively glued with a conductive glue to a substrate of paper, coated with some nickel flake embedded circuit painted onto the paper. And it kind of worked. It was very, very high resistance. And we found we could only make it work for a simple compass chip. We're still working on this. We have a new approach. I won't talk about it in this talk, but watch this space. I think it's going to be cool. But after building these paper planes, and this is sort of about the first couple of months while I was at UQ, I realized, what are they actually good for? And it was around this time that, as it does, Australia caught fire. You may have noticed the smoke around campus. I have carefully arranged this to act as a counterpoint to this talk, so you could appreciate the challenges faced with trying to actually measure things inside a bushfire and dealing with the consequences of wildfires, for example, up in Canada. It's not enough to have a single drone flying around. A $10,000 drone could be in one place at one time taking one measurement. Whereas if you can have 10,000 $1 drones, they can be everywhere all at once, giving you measurements constantly. So our rationale was, if we can build drones as cheap, maybe we can build drones for bushfire fighting that will actually help save lives and prevent losses of properties in circumstances like this. So we thought about it and we realized, well, look, paper's challenging to deal with. Let's roll back a little bit and just go to polyamide. And polyamide is actually a really good material for making disposable drones from. It's light, it's cheap, and it's intrinsically part of the existing circuit manufacturing process flexible circuits are inside all of the cell phones, all of the cameras, all the laptops that we have on us every day of the year. We build hundreds, thousands of tons of these annually worldwide. So if we can build a circuit into it, can we make a circuit act as a wing? And so we thought, well, okay, what's the simplest wing we can build? And we thought, well, how about a samara seed? Maple trees grow natively on UQ's campus. So I tripped over one while going to work one day and thought, oh yeah, I'll build one of them. And so we built the system. It's designed to be a one-part UAV, one part, fully automatically assembled by a machine. And on board, it has a pressure sensor, humidity sensor, an ambient light sensor, a temperature sensor, as well as a 6-DoF IMU, so you can measure its motions as it falls, and then a radio module on the back. And the trick to making these things small and cheap and highly integrated is to make every part of the Buffalo do multiple things. For instance, that leading edge stiffener there is also a counterweight, which provides stability of the aircraft as it auto-rotates. It also is connected to a radiating element, which forms part of the antenna for the system. In fact, it has 3 separate antenna axes, so whichever way it lands, there's always a radiating element pointing up. The radio is on the back of that little circular green part with all the circuits on it. We added some stringers and vasculature, exploiting the multi-material properties of the polyamide. So they're made out of copper. They don't do anything electronically. Instead, they're there as a mechanical aspect. It allows the wing to remain stiff in the directions that we want it to. And that emulates the vasculature you see on a samara leaf. And of course, like all good drones, if it doesn't actually fly, it's not much good. So we built a vending machine on a drone that vends drones. And we paired with our colleagues at CSIRO, who had drones set up at that point, to fly our vending machine and throw them out the back. Before we actually took it to the field, though, we did a couple of quick tests. If you put beautiful glowy lights on it, you can get some measurements about how fast you're falling and how fast you're spinning. And this told us that we reduced our terminal velocity on hitting the ground from about 16 meters per second to about 5 meters per second. And we spin at about 10 hertz, according to our strobes. Alrighty. So here's a view from our drone. You can see they're flying down. You can optically track them if you know what to look for, and you can build a little system that will cue in on your red colored bits of tape there. Sometimes it's a bit hard to see, but on a good day, you can track them all the way from the aircraft to the ground. And that's kind of neat because if you know where you launch them from, and you know where they land, you can calculate what the wind speed is at each point in its descent. One of the problems of building a device that's biomimetic is that when you try to find these things after the experiment, well, they just look like leaves amongst all the other leaves. So I recommend if you ever replicate work like this, paint them bright pink. You'll save yourself so much suffering. Alrighty. Once you do this a whole bunch and you collect a bunch of data, you're able to build up things like topographical maps of temperature, topographical maps of pressure, but also changing wind flow throughout the day. So this is a subsample of our data showing where when we drop it from 4 different locations, 4 different times in a row, the wind has started to change its track throughout the course of the experiment. It's not just enough to build something that auto-rotates. If you have an aircraft and you have onboard sensing, you might as well use it to do something more interesting. And we thought, well, since we have this foldable substrate, and we'd already done some experiments with paper airplanes, why don't we extend that to the circuit board environment as well? And so we started folding our circuit boards into sort of 3-dimensional aerodynamic shapes. And for this orange one, we just stuck with the delta dart because that's sort of understandable to people that know what that is and what it looks like. But you can do all sorts of interesting things like providing corrugated stiffening, forming airfoil shapes, and integrating your circuitry directly into the structure of the aircraft itself. We did a quick experiment on the right there just to show that this poorly structured too-heavy aircraft falls slightly slower if you put flight control on it. It was not a great result of being a flying aircraft. So we went about and designed a much better aircraft. And this aircraft is designed to be launched from a much higher altitude and fly much faster. And here we've used a combination of these 2 bits of work where we have a piece of paper which forms the cardboard shape of the aircraft and then a laminated circuit out of the polyamide which gets glued on. And this combination keeps the cost really low but gives you the best of both worlds. Where do we want to go with this eventually? Well, if you can launch these guys from something like a helium balloon, you could get up to 30 kilometers in altitude. And after free falling for about 10 of those kilometers, you get a pretty good clip. So you could fly for quite a long distance with a glider that's optimized to have a decent glide ratio. But the problem is, what do you do when you're up there? You have wind, you have potential disturbances, what do? Well, if you have a good enough tropospheric map, we want to build a system which allows us to do offline planning to give our system a series of decoupled wavelet functions that allows it to calculate what the ideal heading would be to take it where it wants to go, no matter where it ends up in its flight path, given an almanac of future weather conditions pre-computed using Bureau of Meteorology data. And this one's still in the works, but it looks promising at this point. The idea being that with very, very little information encoded into a tiny microcontroller the size of your pinky finger, you'll be able to actually have something that can navigate long distances with a moderate chance of actually making it there. And even if only one does, they're cheap enough that you could launch swarms of tens of thousands and still carry out your mission. Okay, so let's move on a little bit to drone performance. We've gone from cheap, let's go to good, or at least better. Can we fly with useful loads for longer and further? How would we go about doing that? One of the biggest challenges I have as a helicopter aerodynamicist by training is that helicopters are very efficient, but they're hella complex. They have these swash plate mechanisms with all these moving parts that have to be lubricated and assembled correctly, and some guy forgets a washer and suddenly it tears itself apart right in the middle of doing something interesting. It's a bad look. Drones rule the world today. Quadrotors rule the world because they have 4 moving parts. 4 moving parts. Once upon a time, people thought they'd be more efficient or more maneuverable or this or that or that. No. Actually, they're terrible aircraft compared to helicopters and things like helicopters, but they're so simple. And that really made an impression on me when I realized it. What I would like to do is I would like to build something that is as efficient as a helicopter, but as simple as a drone. How we go about doing that? Well, we thought, okay, a helicopter has one big spinning thing that provides all the lift, and it's more efficient because it captures a larger cross-section of area and can waft it down more gently than a quadrotor with 4 small thrusters that have to grab air and push it down very quickly to get the same amount of momentum transfer. Because kinetic energy is proportional to velocity squared, you're going to need more power in order to do that. So if we just have one big rotor, well, that's great, but how do we get past the swash plate problem? Well, quadrotors use sets of rotors to maneuver by applying direct torque through their thrust. So why don't we do the same thing? We can use a tripod arrangement so that we can then provide roll and pitch, and then have another axis with a slight cant to the side, which provides yaw. If you put these on a thrust cell and just fly them on the ground on a bench, then you can see that, in fact, for the same amount of thrust, you're using substantially less current to make the triangular configuration fly. But on the ground, it doesn't tell you everything. So being able to fly these things is where the proof is in the pudding. And well and truly, we find that actually we're using about 15% less current on our triangular quadrotor. And this is a quadrotor designed to match its evil twin. It has the same mass, same motor mass fraction, same flight controller, same ESCs, same batteries. Even the rotors on the triangular quadrotor have been tuned to exactly match the efficiencies of the rotors on the regular quadrotor's smaller rotors. So of course, it's not enough to be able to fly. You actually have to be able to control yourself. It's gonna work. There we go. So this little one here on the top right is our prototype being flown by one of my students who is a champion pilot. He was a local award-winning helicopter pilot, and he had a hard time with it. His flight experience, oh, okay, now you're doing it. Okay, his flight experience is what he would say as poor, and the flyability was not great. In fact, you can see it's all over the place, and he worked very hard to keep it in the air. And we theorized that this might be because our rotor was using off-the-shelf hobby components for small helicopters that were a little bit squishy, a little bit flexible. So we said, okay, let's switch to one that's really rigid, like super robust. What does that give us instead? So here on the bottom left, we have our rigid rotor. We give it a shot, see how we go. No, that's not going to work. But when you look at the plot, that plot actually made us really excited, because as helicopter aerodynamicists are like, that has a phase lag and it's purely oscillatorily unstable. That looks like gyroscopics. And then we realized conventional helicopters have one big rotor with a pivoting hinge in the middle. Conventional drones have pairs of rotors where the gyroscopics balance out. So we figured, hey, if we put in that pivoting hinge that conventional helicopters have to partly decouple the rotor dynamics from their airframe mechanics, maybe that will work for us. And what we found is that, in fact, yes, that worked quite well. In fact, this is the easiest to fly aircraft we have in our entire lab because the gyroscopics now works for you as a stabilizing reference. Even I can fly it with my 2 left thumbs, and we use it for demos for visitors all the time. So very happy with how that one turned out. But it's not just enough to build something a little bit more efficient. 15% isn't much. That one land, there we go. All right, and that result looked pretty good. If you can save a little bit of thrust, you can start applying optimizations. With a larger rotor, you have a larger chord length. With a larger chord length, you have a higher Reynolds number. With a higher Reynolds number, you have a higher ratio between the inertial flow energy and the viscous flow energy. That means you get a more efficient airfoil for providing thrust relative to the amount of drag that you're generating. And if you can use lower power as a result of that, you can then spin your rotor at a lower speed. If you can spin your rotor at a lower speed, you're reducing your drag, you're reducing the amount of power you're spending. If you're reducing your overall power more, maybe you can move to a different battery chemistry that has a higher energy density and a bit more fragility, so you can't use it in a conventional drone. And since we've thrown away one of the arms of our rotor, our airframe is lighter, maybe we can make them very thin, make them very long, so we can have very small rotors out at the side just to provide the control moments, because all the lifting's being done by the centralized rotor. And it gets better and better and better and better. You pack everything under that motor, you exactly match the motor to the rotor you're driving, and suddenly it gets better and better and better and better until you get an outcome of about 43 minutes endurance while still carrying a 200-gram payload. For comparison, at the time we were developing this, the DJI M100 was still being produced, and it was a 2-kilo aircraft with a 200-gram payload, which flew for 33 minutes. We could also, with our great big rotor, do heavy lift. We could carry a 2-kilogram payload for 45 minutes. We could carry the DJI M100 as payload longer than it itself could fly, which I thought was pretty cool. So does it fly? Yes, look, it's basically just the same flight control law again. It is a different mixing from a conventional quad rotor mixing arrangement, but it is still full rank 4x4 matrix. Unfortunately, you can't hear it here, but because your rotor speed is so low, the amount of noise you generate is tiny. You can hear the birds chirping in the background, you can hear the traffic in the distance, you can barely hear the drone. If you actually want to hear what it sounds like afterwards, please come hit me up and I'll play it for you quickly. But it is very, very quiet. All right. So that's not the only thing we've done in drone design. If you want to carry heavier payloads, but you can't go wide like a helicopter, well, the only other place to go is up. And so we designed a drone entirely limited by the structure of the standard doorway, ostium familiaris, the garden variety door. And so this one is sort of shaped like a flying hat rack, the idea being that we use the biggest rotor above and the biggest rotor below. We thought we would structure multiple rotors in the middle to try to get more efficiency out of it, but because of the inflow velocity impacting the rotors below in the stack, it ended up not being as efficient as just 2 in a vertical stack. It uses some small control vanes in order to maneuver itself. But we don't necessarily have to fly everywhere. Alternatively, we could roll. And so this little guy here uses what's effectively a skateboard steering arrangement to allow it to scoot along the ground using the same control mixing as what's on board the flight control system. So instead of using roll to move left-right, use roll to turn left and right. And the idea behind it was that the flight controller doesn't have to know anything about what its mechanical arrangement is, you bolt it straight on. And it can even handle rough terrain by providing a bit of lift and going to what we call segue mode and doing the sort of the 2-wheel stability across the ground. And of course, it can still fly. At the other end of things, I'm very interested in commercializing some of my work. So I worked with a company called Alaris for a few years to build a truly ginormous aircraft. This is as wide as I am tall. It's absolutely monstrous. It's 25 kilograms and carries 5 kilograms fully electric. It's totally ducted. It looks like a rendering that's actually real footage. We just shined it within an inch of its life with automotive wax. And we were able to meet all of our design objectives for the aircraft, but unfortunately we didn't get continued funding for it. But each aircraft was $250,000 and could take a rifle bullet through one side and out the other, because we wanted to use it for first responder applications where that kind of thing is expected to happen. Now here on the top right, have you ever stuck your hand into a high-speed spinning blade of death and come out with fewer fingers than you went in with? Common problem, and unfortunately it disproportionately affects children because people think that these drones are toys, when in fact they're real tools and they have a lot of energy. I apologize for the formatting of this video. This was done by our commercialization guys. But the idea is that we have a thin plastic hoop spinning around sympathetically with the rotor, just pulled along by a little bit of friction. And this acts as a sensor to detect anything coming into the proximity of the rotor. Before you get to the rotor, you have to pass the hoop. When you touch the hoop, we measure the changing speed of the system, and that allows us to then say, hey, someone's about to touch my high-speed rotor. And at that point, we're able to use an electrodynamic braking system to bring our rotors from maximum speed to full stop in 0.06 of a second. And you don't have to experience what that hot dog there is going through. From the moment of contact to full stop, you get 4 complete revolutions of the rotor. And the idea is it turns an amputation or deep laceration into just a scratch. That's now licensed for being turned into a commercial product. All right, so switching gears again, let's talk about gust rejection. If we're flying around urban environments with our cool robots that now fly for a whole bunch longer, how do we avoid things like wind pushing us into obstacles? We don't want to collide with things. We don't want to get pushed off course. So when we react to gusts, the usual way of doing this is to have a really good sensor measuring our position, having some sort of control law based on detailed models of your aircraft aerodynamics, your rigid body dynamics, maybe some measure about the wind itself if you know its nature. And then we apply computed corrections to actuators to bring us back onto the trajectory we want to be taking. The problem with this is you have to be displaced before you can react to it. You don't actually know you're off course until you're already off course. And you can only be as good as your sensing is. If you have something like GPS, you may not have the spatial or temporal resolution to provide you any degree of security around obstacles. INS, of course, famously drifts, though RTK GPS is a good stopgap, and things like pitot tubes are completely useless in low speeds. Of course, IR optical tracking provides excellent results, and UPenn is very famous for their application of IR optical tracking. So I want a quick shout out to that. I call it the pink cheating room because early infrared emitters were picked up by cameras as a big pink glow. And it's great. It's a fantastic system, but it doesn't really work outdoors because it must compete with our old adversary, the sun. I don't know about you, but I'm still formulating my plans to defeat the sun. IR tracking is fast, it's precise, it's flexible. It's not especially cheap, but it's really easy to work with. So it's a great sensor, except we can't use it. So what do we do instead? Well, how about we use the aerodynamics we already have? We know that if we're flying, we must have air to work with. So if we use wind over the rotor blade moving towards the oncoming wind, which increases the amount of lift and drag, and then we use the wind across the retreating blade, which is moving away from the oncoming wind and produces less lift and less drag, to produce a total net force that we can then measure, maybe we can use that as a sensor because that's linearly connected to our drag thrust through our velocity and also our pitch velocity, but that's a more subtle point. So if we put some sort of sensor beneath our motor, we can measure that changing thrust force at the end of our blades and use it as an input. To build something that look a little bit like this, we shamelessly ripped off Rob Howe's work on embedded pressure sensors in polyurethane material. Rob knows what we're doing and approves. We thought it was a great approach because it's very compact, it's very lightweight, and it's very precise. All things you want when measuring thrusts on a drone. It sits between the airframe and the motor, and it's surprisingly good as a sensor. So here we have it rigged up on a lever beam with one end having our JR3 load cell, and then the other end has our force sensor with a water load being poured into it at the end. And the ratio between our rotor displacement and our lever arm are designed so that the overall magnitude torques being measured by our 2 load cells should be the same. And in fact, they track so spot on, we thought we made a mistake at the start. But you can actually see the JR3 is able to pick up a couple more high frequency characteristics in there, probably because of us pouring water in as we go. So stick a rotor on it and throw it on a swing arm. The swing arm provides us an easy source of repeatable velocity in a lab with limited size. At 0.53 meters per second, you can see we get a very clear signal on the green one there, and the cross-flow sensor picks up basically nothing. Though they're not scaled the same, the force being measured through the vertical thrust is the one there in red. So when you turn on your thruster, you can see you start developing some thrust, and then you get this component as the swinging begins to turn on. And it's really precise. We can actually use it to detect the ambient airflow due to air conditioning. So we got these weird periodic oscillations as we had our swing arm going around in circles. We couldn't figure out what they were. And then it occurred to us that they always happened when we were heading in one particular direction. No matter how we oriented the assembly, that bulge always occurred in one direction. And one day, the air conditioning wasn't on, and we didn't have it anymore. And we realized we're actually measuring the tiny, minute amount of crossflow through the lab because of the air conditioning system. So, okay, that's cool. What if we put it on an aircraft now? It's not enough to just have force torque measurements. We actually want to turn that into something that gives us the drift velocity of our aircraft. So if you have force sensors on each of our little motors, you can decompose that to a triple of force in each direction. You can then put that through a 12x6 matrix and do the pseudo inversion, and that gives you out a velocity vector at the end, depending on all of your sensor inputs. This wasn't something we tried to do on board the aircraft. This was all done off board on the aircraft, and the version you see here was just streaming it all to an off-board computer to keep the computation load low. But it worked very well. And what we found is that our velocity estimates relative to what our OptiTrack system was giving us was pretty much spot on. And you can see here we're flying in a circle. You've got the dx and the dy components on left and right there. The blue track is the one that we're estimating, and the black one is what our ground truth is telling us. And during the flight maneuvers, it looks pretty good. In fact, the only deviation there is when it's taking off and when it's landing, where ground effect is coming into play. If we have it do a more dynamic maneuver where we start doing a tick-tock back and forth, we get a little bit more of an excursion there because our rotor model doesn't take into account some of those higher order effects. But if you look at the overall linearity between the overall ground truth velocity versus the estimated velocity, it's really nice and linear with one single data point hanging out in space, which we think was just a communications error. All right, so if we can make them small enough to fit under a drone rotor, can we go further? We would actually like a pure aerodynamic sensor without having to have a rotor on it. What if we build a bunch of whiskers? And so we took the same principle. Instead of having 4 sensors on a platen, we could get up to 12 sensors as sets of 3 each. And on top of that, we put a little piece of laser cut flexible acrylic, and then we put a dab of, I believe it's ABS, which we then extruded in like a taffy pull to produce a minute little whisker. And these little guys are quite small. They're about 1 inch across the diagonal there. And they're kind of cute. In fact, you can have fairly high forces and fairly low forces. So this is an example of us having our sensor and just dragging it across the surface of the LCD screen that's displaying the real-time output of our sensors. And this is scaled so that the magnitude of the forces are quite sensible. But you can see that even when the whiskers are removed from the display, they'll ring a little bit, measuring their own mass as they go. There they go, direction and magnitude. And we can have arrays of up to 250 something of these as part of a USB network. All righty. So of course, back on our swing arm, let's see how these things work as fluid velocity sensors. And the answer is that weird little wobble is back. This time we made sure the air conditioning was off. It looks like a beautiful linear trend, but what's this wobble? Well, it turns out that every time our swing arm passed a particular position, about pi radians, we got the minimum of our wobble. And we believe this is because our sensor was mounted slightly off axis, and it's the weight of the whiskers were flopping one way, and as it swung the other way, the weight of the whiskers flopped the other way, providing this sinusoid superimposed over the magnitude of the sensor. And as we reoriented the frame, it actually didn't matter what was going on because it was about the sensor relative to the swing arm axis. But the fact that it's beautiful and linear is very reassuring to us. But it's also supremely sensitive as well. So it's a little bit hard to parse what's going on here. But you see that we have a plate moving towards our sensor, and then at some point the red light comes on. That red light comes on when it senses a threshold of force above a necessary condition, whereupon it says, aha, something is approaching my whisker. And we're actually measuring here the bow wave of air being pushed ahead of this hand-sized plate of paper coming towards our sensors. In fact, we can measure forces down to 3.3 micronewtons in size. It's about the weight of a flea. So very, very sensitive. Okay. Since we realized we can actually measure the effect of aerodynamic flow around an aircraft without even touching it, without having to touch the environment, we could get some reciprocal pressure field we can deal with. We realized, well, why don't we turn that into a sensor for an aircraft navigating? And aerodynamics is always available. Day, night, over land, over water, in smoke, in fog, it doesn't matter. If you can fly, it's there. So by understanding these effects, we could build a system that might allow our drone to not require any other sensors. So this was an attempt to build an aircraft which had a ground effect system. So a set of shaped channels would allow the rotor outflow of two slightly canted motors to interact in such a way that it produced a restoring torque back to the middle. What's the correct combination of angles and sloped plates? I don't know. But let's do an exhaustive search across all the possible angles it could be. And what we found out is that it's pretty clear the higher angles you have, the more restoring torque you get. Here on the right-hand side, you see the red ones are the ones where the drone flopped around and escaped, and the blue ones are the ones where it settled down into some sort of stable equilibrium. And we could tell that actually, yes, there was some sense to this. These interactions could be strong enough to stabilize our aircraft. But we learned early on that, in fact, we needed to make sure that the control on that aircraft is very, very clean. And even the effect of changing the velocity of the rotors would be affecting the amount of voltage on the rest of the battery, which then changed the dynamics of the rest of the aircraft. So we actually regulated the entire power supply for this aircraft, all the motors, all the controls, every electronic system fully regulated to have just a few millivolts worth of ripple. So everything was extremely clean as a power system. And this let us do a really interesting thing. If we take our drone and we set it to about 95% hover thrust and just drop it, it descends down, touches the ground, maybe doesn't touch the ground, comes into ground effect, and bounces until it reaches some equilibrium altitude where the effective ground effect is enough to compensate for the reduction in thrust necessary for it to fly. And it reaches this beautiful equilibrium. And here in black, in this top left, we've actually mapped out what our simulated result was, and our blue results match pretty well. One of the things we discovered, though, is that in doing the simulation modeling, we had to change how we understood the ground effect model for an aircraft like this. If we use the original Carpenter and Fritovich model here in black, our rotors would be too small. They just wouldn't provide the right amount of power saving relative to what the size of the rotor should be telling us. But if we changed our model to treat all the rotors of the drone as some sort of meta rotor with the tip-to-tip distance across the two pairs of rotors, then it actually matched perfectly through the middle there. And I think that tells us something a little bit fundamental about the fact that the rotors of a drone are all interacting with each other in a way as well. Alrighty. So taking all of these things that we've done and then glomming them together is one of our current pieces of work. We've got an aircraft now which implements what we call an electronic force controller. The electronic force controller is not controlling speed of our rotors, but actually the force being generated through a fast feedback control loop at about 1 kilohertz. We can measure the amount of thrust being generated in real time, turn that around, put it through our aerodynamic models, and then produce an output control. Each of our EFCs is basically a flight controller unto itself. Each one has its own IMU, and they talk to each other through a daisy chain to minimize any sort of bottlenecks in their communication. So it's a lot of processing on board to do this aerodynamic mapping, modeling, and disturbance rejection process. Each of these can each take 2 additional whisker boards so that we can measure the ambient flow field around the aircraft and then measure the changing aerodynamic model as the aircraft approaches something like an obstacle. This one's reasonably recent work. I'll just throw that in to show that, yes, even if it's got changing loads in aerodynamic environments, it can regulate its speed to maintain the same thrust. Let's move on past that. Okay, so if we want to fly close to obstacles and respond accordingly, we need to know what flying close to an obstacle looks like to one of our sensors. So we built a rig which allows us to fly close towards an approximation of a wall or a corner with ground or ceiling effect. And by setting this up to be an autonomous system, we could log a stupid amount of data points over a long period of time and let the algorithm crunch it for us. It's about 500 millimeters of travel there. If we then map what's being measured by each of our sensors against its position away from the wall, we get some curves, which are pretty instructive, I think. If we have the free air case where we just translate our rotors without actually being close to anything, we would expect to see something that's roughly constant, and that's what we get. If we come close to a wall, we see that we get a small amount of changing flow. And this is because as the rotor approaches a wall, some of the air being sucked in above and pushed out below has nowhere to go out in the space blocked by the wall. So it just sucks itself back in again. You get a recirculation effect. As a consequence of this, the rotor believes that it's producing less thrust this side and moving in the opposite direction from what the wall is actually doing. If you then exacerbate that with a corner effect, the effect gets stronger because now you're blocking that rotor on multiple sides, and so the effect becomes more pronounced. But something really interesting happens if you add in ground effect. Suddenly, you go through this period where it's getting worse and worse and worse, and it gets more normal again? That's strange. What's up with that? And I got to tell you, I just don't know. We're trying to understand it still. But if you change your distance away, so you're now more like 3 rotor radiuses away above the ground, you see the same sort of thing, but even more exaggerated. So we don't know what's causing this. This is open to us still. We're keen for any insights you may have. But the important thing is what's happening in this part of the curve. You can see that for all of these conditions, you always have a widening away of the sensors indicating a divergence from what your anticipated flying conditions should look like. So we can use that as a signal to drive our system away from obstacles. So where we want to go with it is to have a system whereby which we can navigate blind through a smoke-filled room using nothing but our rotors to keep us from crashing into anything. All right, just to finish out, I want to talk about something completely different. But when I say it's completely different, it's similar, but not quite the same. So I want to quickly talk about 2-legged walking machines. Anyone who knows me knows that I got into robotics because I wanted to build giant war machines to crush the cars of my enemies. I'm not even kidding about that. I think that's written on my business cards. Walking robots are challenging to build. They require extensive modeling, estimation of ground contact mechanics, expensive sensors and actuators, and all of this adds up to be very expensive. Things like Boston Dynamics robots are amazing. I can't afford one. Maybe you guys can. I can't. And we do all of this hard work just to stop the thing from falling down. But I'm a helicopter person. That's my background, my experience. And helicopters control themselves. They don't fall down. They use this rotor, which generates forces and torques to keep them in the air. And they're able to avoid aerodynamic disturbances pretty well. So what if instead we treat our robot as if it's a helicopter with disturbances coming in through its feet now, and some sort of force torque generating a system to keep them upright? How are we going to do this? Well, we're using a technique called control moment gyroscopes. Unlike a reaction wheel, which you just accelerate the wheel or decelerate the wheel to get a resultant torque, we have a high-speed spinning wheel, which we then tilt. And the corresponding precessive torques generated by tilting that wheel provides a 90 degrees phase-shifted resultant torque that you can work with. And we can use it as an actuator. So if we build one based on our basic knowledge of second order dynamics and control, run through the math, how much space and how much weight and how much things you're going to have, about 10% of the mass of the vehicle is put across to the flywheel. Let's see if we can make it work. You get something that looks a little bit like this. It's about the size of a chicken. We call it the tiny giant robot because we want to build a giant robot, but our budget doesn't extend to that. And it's about 4,240 Australian dollars for a dynamical biped. In freedom units, that's a bit more like just under 3,000 US dollars. All right. So what's under the hood? Well, we have the flywheel as spoken about before, but the feet, the ankles are completely floppy. There's no reaction torque between the ground and the rest of the robot. The flywheel's responsible for doing all of the balancing. And because it's so cheap, we're just using off-the-shelf hobby servos. So how does it walk? Well, it basically puts one foot in front of the other. All the orientation controls being done by the CMG. We just compensate for the fact that the center of mass is moving with respect to the ground contact. And to turn, we just apply a small angle to the feet as it rotates during the single leg stance phase, and that allows it to change its heading. So the dynamical model is really straightforward. Second order dynamical system, PD control should be good enough. Bearing in mind, we have those forces coming in through the leg contacts that we can compensate for by basically doing a feed forward compensation. So of course, we're good at kinematics. So kinematics is straightforward. We can calculate it as a whole bunch of basic trigonometry and feed it into our control system. Control architecture looks a little bit like this, with a fuzzy box called bias correction, which I won't talk about this time around because we don't have enough time. Suffice it to say, it's one of the more squirrely parts of making these work. All right, simulation. Simulation says it should function. It has a neat little effect where, because of the way that our bias compensation goes, if you pick up one leg, it tries to balance itself over its singular ankle. And it looks like this when you build one in practice. So here it's wobbling around. It has a little glitch sometime around now where the communications system thinks it is instantaneously 45 degrees away from where it actually is. That's just a data bus glitch. We fix that in the future. But even with that small little error, it's able to reject that effect and keep balancing quite happily. Fast forward a little bit after we've fine-tuned it. Now it doesn't shake quite as much as a startled chihuahua. We now have a system where it can balance. We can apply loads to it. It doesn't know anything about the nature of the loads being applied. And for a vehicle of this size, a 9-volt battery is pretty significant. We can change the ground underneath it. And again, it doesn't know anything about it. Ground angle doesn't matter. And we can even do neat things like shaking the ground to emulate an earthquake. And it just responds sensibly. He doesn't care. It's great. Of course, standing still is not especially useful. So we then have it doing in-place foot switching. And you can see here, it'll then shuffle forward a little bit slowly. Now, the reason why we don't move more quickly is because we found there was a design flaw with this version of the robot where the center of mass of the feet below the ankle pivots was too low. And so as it moved its leg forward, its foot would rock back. It would get caught under its own feet if we didn't have some way of preventing that. You can see here we're able to turn as well and walk around. Nice. The GoPro there does nothing. It's just a counterweight. But if you're not moving forward and exciting that coupled mode, you can get pretty reasonable leg lifts. And this sort of shows what this early platform is capable of doing. So we get about 30 centimeters clearance during each leg lift. All right. So where are we going in the future? Rather than continuing to spend energy on this particular version, we put him in a museum, and now we're working on TGR2. And TGR2 has a very different torso structure to be more compact, using a 5-bar spherical linkage. If you know anything about spherical linkages, I recommend you never ever attempt to do this. It is a source of unending nightmares. But you can't beat the price. It's now less than 2,000 Australian dollars, which is about 1,350 freedom units, which I think is pretty good. We've moved away from our aluminium enclosure with a steel safety band because This thing has the energy of a rifle bullet inside of it. And we've also moved to a much cheaper gyroscope structure. So I'm well and truly over time, so I'll stop showing you more of these things, but it should look a bit like that when it's finally assembled. Okay, so where to from here? A couple of minor upgrades to be done, demonstrate walking, cliff detection, all the sorts of things you do with a walking robot, and hopefully in time building a less tiny giant robot. Other stuff going on in our lab, we are looking at rotor arrays for fluid entrainment efficiencies. We're building virtual reality peripherals to allow you unrestrained walking inside a closed environment, building quadrupeds using dynamic deep reinforcement learning, measuring the depth of boreholes. We have the world's most precise borehole depth measurement system, doing stuff for historical robot recreation, because Hero of Alexandria built robots once. We're building them too, and many, many other things. So quick shout out to all the people who've made this happen. It doesn't occur in a vacuum. I have a small stable of highly skilled, highly qualified academics and technical staff who make it all possible. We're a very small lab, all things considered, especially when you consider the breadth of what we do. But I'm very blessed to have the contributions of so many talented people. And with that, thank you.
All right, that's fantastic. We've got our two panelists, Spencer or Fernando, who's gonna?
Yeah, I'll go first. Yeah, so this was a fantastic talk. I love when people present hardware. I think that's very exciting videos. So this question might be a little surprising. What do you think the role of simulation is in your work? Because you consider a very complex phenomena, especially aerodynamic phenomena. So how do you use simulation in your work?
This is an excellent question. Simulation, like controls, like algorithms, like a screwdriver, is a type of tool. And the question is, what do you hope to get out of that simulation? I have gone at times right down the rabbit hole of building very sophisticated simulators. And other times I've done a first order thing just to make sure the time constant was correct. In both cases, I learned something useful from that. I had a paper recently rejected because we were using tertiary aerodynamic effects through vortex interactions in a rotor array to try to get small amounts of efficiency out. And the reviewer said, why haven't you simulated this? And the answer was, because to simulate it effectively, you will lose the fidelity. You only get what you know should exist in your simulation, unless you're able to capture the full depth of it. Something like CFD, if you don't construct it properly, you don't know if you're getting something real. You might get something that says shouldn't be there, or you might not get something that it says should be. And even worse, when we complained about this, the reviewer said, well, why don't you have a closed form analytical solution? And the answer is because I can't solve the Navier-Stokes equations. And if I could, I wouldn't be submitting to your journal. So the question is, what are the assumptions your simulator is built on? What is it telling you? And the answer is, I use it at lots of different levels.
Okay. No, first of all, this was an outstanding talk. And I want to remind people on Zoom that you can use the Q&A button to submit your questions if you want. We will read them loud here in the auditorium. So one of the questions I had is that in your designs, you are proposing that increasing sizes of rotors is the best way to increase efficiency. And you are showing these models that have very long arms to counteract the effects of the rotor. My question is, how do you address vibrations with these designs? Because these long arms are going to reduce your natural frequencies for the system.
Yep, that's an excellent question again. So if you have a long arm, you get this little thing wobbling around on the end. And that's good and that's bad. That's bad because you've got a vibration being generated. But the length of that arm actually reduces the speed of that vibration a great deal. And if you know what it is, you can always filter it out. But with that wobbling bit on the end, you also have a rotor attached to it. And that provides vertical inflow damping, which causes that to reduce. And so what we found is actually not a big issue. We build the thing, we fly it. Yes, we can see the oscillation associated with the arms doing a little dance, but it doesn't impede its ability to do flight control. Interestingly enough, if we had very skinny arms that were much shorter, you'd see much more of that, just because you'd have a different frequency that would get closer to the dynamics that you care about, or aliasing on top of that. So we don't see it as a big deal. We've flown a few of these aircraft now. It's never come out to be a problem. As you get bigger and bigger and bigger, though, you absolutely do have this problem that now materials is no longer working for you. Very small things are just innately rigid. That's just the way they are. The strength of the materials versus the masses you're dealing with are in your favor. As you get larger, things become much more flexible, and you have to plan for the fact that your systems will diverge. A bigger worry to us was torsional motion of those alarms, that our little rotors might actually be inducing a wobble that we couldn't take out. Turned out not to be a problem, but it was always an anxiety.
And, another follow-up question is we're talking about wind rejection, and usually when you increase the size of your rotors, you are targeting lower thrust-to-weight ratios, and that also affects your wind rejection capabilities. So how do your designs deal with like wind rejection?
Excellent question again. You're hitting all of the nails on their head this time around. So when you build a large rotor with a low disk loading, you're basically building a sail. Or think of it as a sailplane that flies around in circles. And sailplanes have the word sail in them for a reason, because they get pushed around by the wind. You've basically got a large wind-catching device and a very low weight attached to it. So you're going to go with the wind if you don't do anything about it. You don't have the ability to make small corrections all the time. What you have to do is basically point yourself into the wind and stay there as best you can, and almost sort of surf the gust as it comes. Being able to detect that early on is really, really important, which is part of what motivated us to say, how can we detect these wind gusts before they destroy everything we're doing? So though it looks as if all of these things I've talked about are not entirely connected to each other, each one gives rise to the next thing that I've discussed, except for the bipeds. I've been dreaming of that since I was a child. I still have ambitions. So yes, wind sensing is fundamental to being able to go and do those big corrections to stabilize yourself.
Anybody have any questions?
Great talk, thank you. You only mentioned this at the very end, but I was wondering what led you to looking into recreating Hero's inventions and what you're hoping to learn from that.
So the Hero's inventions part actually comes from a colleague of mine who's now working at the University of Exeter. He had a collaboration with the Uni of Exeter preceding that, where they're actually antiquarians. They're interested in historical technology. And so Hero of Alexandria's inventions, we all know about the Aeolipile, the little steam engine. A lot of people don't realize that he also built robots. And one of the very first robots he built was a mobile shrine. And the shrine was able to roll along a track, come to a stop, have a little set of maenads, little like nymphs or spirits, do a little circular dance, and then dispense wine and milk from a statue of Dionysus. And then it would turn around, do the same thing in reverse, and then roll itself back, which honestly, Hero is just flexing at that point, right? Whether or not you can build these systems has always been a matter of debate, because you never quite know if they're just putting on that they can do this, or if it's actually a thing that was built. So they came up with a model in SolidWorks of what they thought it would be like, and they took it to us as actual engineers and said, can you build it? Dude, yeah, of course we can build it, right? But the catch is you have to use historical tools and processes to do it. And we quoted them a price of what it would cost to do that, and I said, yeah, look, just build us a model instead. So we built them a model about 40% size, which looks amazing, and they now have an exhibition on. You can come visit it at UQ next time you're in Brisbane, maybe next week, I don't know. And yeah, it was all about applying modern robotics techniques and knowledge to how the ancients had done something. It's not something that's on my critical path of research, but it was such a fascinating thing to study.
We have an online questions. Jake is asking, it's saying, thanks for the very interesting talk. Building custom hardware takes a lot of time and effort, as you may know. In your work, how do you balance the need to build a minimum viable prototype versus the benefit of designing something with more long-term reusability for future products and experiments?
Yeah, there's an innate wisdom in that question. I'm a terrible scientist. I'm like the worst. I should be publishing all of this stuff. I've shown you a whole bunch of stuff that's actually not published. Please don't rip it off. We'll get there eventually, right? But I wake up every morning and I think, hot diggity damn, I'm going to build the shit out of something. Like, I love building. It's what I'm here for. So the real question is, how do we stop Pauline from building something and actually publish? So for me, there is a combination of valencies to this question. Some things like our aerodynamic force sensors, we spent the time, got it right, and we had it perfected, partly through to our intent and partly through to sheer random chance it just worked out. And we have used it for experiment after experiment, paper after paper. Some things like the TGR, we realize small changes have large impacts on the overall mechanics of the design. So fine-tuning one design is actually counterproductive when we should be improving many things. So we're not dealing with this moving target problem all the time. And so we've iterated that a bit more than other projects. Normally we build it once, we get it right, and then we shelve it. The notable exception is actually our triangular quadrotors, where they just fly so well. It's weird. The big one I showed, which is about 1.5 meters around, is too big to fly regularly, but the little one we still keep and we still fly as a demo. So we try not to overinvest. We try to go for minimum viable product, but we're rationally invested in it, so it ends up being pretty good. Every single one of our robots, I don't know if you actually could see, let's see if I can show you. Yeah, this one. Every single one has our motto on the left. You can see it, finest handcrafted robotics. We do it because we love it. And yeah, we're terrible scientists. Please cite us. We could really use them.
So I'm curious about the wind sensing. Can you sense a differential, like if instead of a pure going all the way across the vehicle, I mean, between ones within the if you've got some type of other more weird flow, are you able to sense that? And have you done that? And what use would that be?
Yeah, so each of our independent whisking elements is its own sensor. So that little array of 4, you have 4 independent measurements. So if you have a difference on one side of the board from the other, you'll pick that up as being a changing magnitude or changing angle. If you built a big array of them, you'd pick that up easily. We haven't done much with that because we've sort of been saving off on doing that until we've got the aircraft type platform working, where we can do more sort of applied stuff that's easier to justify to the funding agency. But we would love to just build 100 of these sensors, cover a surface, and just blow wind across it and see what happens. I think that'd be super cool. It makes certain aerodynamic measurements and experiments way simpler, but nothing stops us from doing that. We had a bit of interest from petroleum at one point, who wanted to put them in tubes to measure multi-phased flow, so combinations of fluid and gas bubbles, and asked if we could detect that, and we were very confident that we could. We've also tested it in water, and it worked just amazing in water, and there's a consumer product coming through the pipeline on that one.
Go, I don't know if so I have a particular question for the EFC. I think it's a very clever idea, and you said that you have the different models interconnected to send information between them.
Yeah.
I wonder if what are the frequencies that they're using, and if how are you rejecting the coupled effects in between them?
So when you say the frequencies they're using, can you elaborate which frequencies?
Yeah, so you mentioned that the controllers themselves are working at a kilohertz ratio. Is this communication in between the models working at the same frequency, or it's like a cascade controller where?
No, they run slightly slower. And the reason they run slightly slower is because we're limited by the speed at which we're getting, or frequency, I should say, the frequency at which we're getting our IMU measurements. So we have a 400 hertz IMU, a kilohertz rotor force measurement. So we control our rotor at a kilohertz, but we communicate to all other platforms at 400 hertz because that's the speed of the slowest sensor we have. And they all talk together at that speed through a megabit link. I think actually it's a 12 megabit link between them all. And they're able to update each of their measurements very, very quickly through a little algorithm we put together to try and minimize the amount of data transfer, because bottlenecks of these systems are what kill you. So they're each able to make their own independent decisions based on the most up-to-date measurements they have at each point in time. Yeah, it's technically a multi-frequency control thing, but practically the dynamics are not so fast that it makes a difference.
I'd like to go back to the whiskers.
Sure.
So my question is, have you thought about how you're going to place them on the UAV to sort of minimize the effect of the rotors on those measurements, since they are so sensitive?
I got to be honest, this is one that still keeps me up at night. I mean, that and memories of high school, but my plan is to have little stalks with our whiskers sticking out at the end, but there's a couple of different things we want to measure. We want to measure the far flow field. We want to measure the close flow field. So having a couple directly on top of the drone and directly underneath the drone is also in scope. We haven't fully hashed that out because we're trying to get the hardware to work still to integrate everything. Once we have that, then we'll have a bit of a think about what the natural places to put these sensors are. We have an algorithm we've developed, which is able to take arbitrary position placements on a sphere and then map what the expected flow mechanics would be in terms of sensor value displacements. So it actually doesn't matter in terms of the analytics happening under the hood, where we stick them, as long as we localize them correctly within our model and then feed the equations back in reverse, we should have something useful pop out. But the key thing is some places will be more exposed to noise or vibration or ambient flow field generated by the rotors. We actually want to get away from those as much as possible. But there may be benefit in being able to detect what that flow field looks like as an independent observer of what the rotor thinks is happening.
They're a part of the talk. The Samara one, have you thought about having powered maple seed flight?
Oh, we've definitely thought about it. And so has everyone else, which sort of disincentivizes us from doing it a little bit. We are avowed neophiles of a sort. We're very interested in something new. And as soon as somebody else does it, sort of the joy goes away to a degree. We have definitely thought about it, though. We've considered in a couple of different ways, applying pulsed thrust to provide some sort of cyclic equivalent control, applying direct counter torque so that the whole thing just sort of swirls up with basically using it as a mixer rather than as a thruster. But if you're going to do that, you might as well generate direct thrust upwards as well. Having articulated cyclic control in terms of servo tab or something like that. Really, the possibilities are endless. There's one I saw recently where they had a vertical thruster off axis and used similar to what I said with the mixer, but instead having a component which would always generate a pitching torque, which gave it a higher coning angle. I don't know what the use of that was, but it was cool. Because there's this big space where people have been searching it out, we're not interested in the dynamics of Samaras. That's been done. I think there's a Nature paper on it out there now. We're interested in making them cheap. And this is just a mechanism to allow us to build a one-part UAV. I have plans for something similar, but it looks nothing like a Samara, but it would work very similarly. But you'll have to wait.
All right, any other questions? Okay, well, let's thank the speaker one more time. That was fantastic. Okay, so this is the last Grasp on Robotics seminar for the spring semester. Details regarding our Grasp on Robotics Fall 2023 seminar series are coming soon. For more information on upcoming events, be sure to follow us on social media or check out our website. Thanks again and have a wonderful day.
Thanks.